So we do have time for some questions. So if you have a question, pop your hand up, and my colleagues Sophie and Zosha will come to you. Should we go with this guy in the red hoodie first? While we're waiting for him to come there, at the risk of, I had a dinosaur scientist, and I annoyed him by asking him a question about Jurassic Park. But films like Interstellar, where we see depictions of black holes, do these meet your approval? Do they?
Ooh, that's a good question. So it's taking it in a whole other direction, but paleontologist, and I wanted to be a paleontologist before Jurassic Park came out, so before it was cool. And I love the Natural History Museum. So I would say that actually most of it is accurate. So actually, Christopher Nolan did a fantastic job with that film. And if you want to learn more about the effects of general relativity, how time can be stretched and warped, honestly, it's a really nice kind of entry point into that. I would recommend it. But the accretion disk around the black hole is not accurate. So I have a YouTube channel, by the way, shameless plug here, where if you ever wondered what it's like to fall into a black hole and what you would see, I've made a virtual reality movie of it. So if you Google my name on YouTube, you'll find it. So it's really cool. You can put it on your phone like this, and you can look around as you fall in. Sorry.
No, fantastic. So we've got a question up here.
Okay, so quick question about, so I've always been wondering about the difference between black holes and wormholes. And is there a difference, or do you think that wormholes even exist? Or
No, that's an excellent question. So there are a lot of people working on wormholes, and one of the reasons is because even actually in the movie Interstellar as well, one of the simplest wormholes that you might have heard of is called like an Einstein-Rosen bridge. And the idea is that black hole has to lead somewhere, right? But you don't want to get crushed by it in the singularity. So if you have a wormhole and you're able to stabilize it, you get a finite throat that you can travel down, and you can end up in another part of the universe, because space-time is curved, so you could just curve the universe. There are people who are taking wormholes seriously, because they're a way to resolve problems with black holes, like, oh, there's an event horizon. Well, if there isn't an event horizon, then you don't have to worry about that, causal boundary. And so, people are working on it. But what I would say is that our calculations and observations seem to show that, at least for Sagittarius A star in our galaxy, it's probably not a wormhole, because the wormhole would have a diameter which is too large compared to a black hole, from what we see. Also, it's really hard to stabilize a wormhole, to keep it open so you can travel through it. Because the last thing you want to happen is as you're traveling through it, it collapses, because then you're going to get crushed into nothing, right? There's no space or time where you get crushed into. So it turns out that wormholes, they're actively investigated, but we're actually starting to rule some of those models out. But I hope that they exist, because they fix a lot of problems too.
Lovely. We'll go to the front here, and then Sophie will go up to the blue and white T-shirts.
What about white holes?
Ooh, so you got me on a hard one here. So a white hole is almost like the opposite of a black hole. So black holes swallow, and white holes spew out. So it's almost like the inverse of a black hole. So far, there's no observational evidence that we see them. We tend to see that all of the black holes that we can see, and it's not actually that many yet, so maybe in the future this will change, that all the black holes seem to swallow up matter. But if we saw the opposite, for example, we saw a very dense object in the center of a galaxy, or maybe something that, is got a star nearby, and instead of all the matter falling in, it's being flung out, then maybe it's a white hole. And some people think, so some scientists think, that black holes and white holes are connected, and on the other end of a black hole, if you travel through it all the way, you'll come out of a white hole.
I was wondering what would have happened if all the black holes in the universe disappeared.
Oh, that's a really good question. And you know something? So what I will tell you is that when everything else goes, when all the stars eventually die, when the universe keeps expanding forever and it gets really dark, the very last things that will be there will be black holes, right? And black holes, they evaporate. So Stephen Hawking found this out. He found this thing called the Hawking temperature, but they evaporate really, really, really slowly. So like, for example, if a black hole weighs the mass of our sun, so that's actually a small black hole, so one solar mass, it would take 10 to the power 66 years to evaporate completely. So that's million years. So, and that's just the small black holes. So actually, black holes will be the last things to survive in the universe. So,
Okay, we've got a question on the front here.
What happens if you fired Voyager 1 into a black hole?
now, I'm doing an experiment in my head right now. So, did you know that actually, you hear all these stories about spaghettification. So it's like, if you fall into a black hole, let's say feet first, you're going to get stretched like spaghetti, right? Well, if the black hole is really, really big, so if it weighs at least 10 billion times the mass of our sun, so like this M87 black hole that we talked about today, then the tidal force is very weak. What does that tidal force mean? It means that the force of the pulling between your head and your feet would be about Earth's gravitational pull. So it'd actually be really comfortable. So you could fall into a 10 billion solar mass black hole, and as long as there's no matter burning you and ionizing you and so on, you actually find that you can cross it comfortably, and you wouldn't even realize you crossed that event horizon. So it depends on which black hole Voyager falls into. So...
So if we had an option, you want to go for if I'm going to have to fall into a black hole,
bigger,
I want it the biggest possible.
Exactly.
If
Bigger is better in
for some reason
this
it's
case.
like 3 doors to choose from.
No, the biggest black hole is the best. And there's even papers where people have said, could you actually have habitable planets within the event horizon of ultramassive black holes? And the answer is, in principle, yes.
Thinking about it, if I was floating in between 3 black holes, would I not even have any choice? Would I just get sucked towards the biggest one?
That's a very good question. The answer would be yes, but those little ones, they have a much stronger tidal force, so they could scatter you out completely. Mm-hmm. So it depends on how they're distributed, but ultimately the big one is going to pull you in. Okay.
We've got a question up here.
Okay. Are black holes 2D or 3D or another dimension?
Ooh, now that question cuts at the very heart of what a lot of mathematical physicists are working on today. So, okay, Einstein tells us that black holes are what we call 3 plus 1D, so it's like 3 space and 1 time, so they're 4-dimensional. So Einstein's theory is a bit weird because, in our day-to-day life, right, we experience the spatial dimensions, so like, we can move in 2D very easily, right? And in principle, we can jump, we can move in 3D, but we can't fly. But we don't control time. Time for us just passes by, right? We can't move backwards in time, we can't move forwards in time too quickly. But Einstein says, look, time isn't special. Time should be treated in precisely the same way, mathematically, that we treat space. And so black holes really are 4-dimensional objects. And that's a very weird concept. And there are a lot of problems with black holes, like the singularity that we talked about. So if the black hole isn't spinning, the singularity is a point. So there's an infinite amount of, so it's infinitely dense. But if the black hole is spinning, the singularity is no longer a point, it's actually a ring, which is even weirder. And so we don't really know what's going on there. And so some physicists are thinking at looking at black holes in higher dimensions, because as higher dimensions are sort of like the extra dimensions give you an extra degree of freedom for some of the weird stuff that we can't explain to be explained away through, basically. So it's actually a very good question, and a lot of people are working very hard on that maybe black holes exist in more than 4 dimensions.
So how would the supermassive black holes form? Because it takes it's not possible in this present day for supermassive black holes to form. So there must be something back then that could have happened.
That again is an excellent question. I do this for a living, and I give talks at conferences with leading experts, and the questions I'm getting today are actually more pertinent than the questions we have in some of these meetings. So your question is also a great one. I'm not just saying it to be nice. All of the questions are great. So this question is actually also, it's a big issue in modern physics. How do black holes grow to be so massive? So just to set the stage a little bit, we know that the universe, from cosmology, we know this quite precisely, that the universe is almost 14 billion years old, right? And we know it took millions of years, really, for the first stars to form. And then stars can live for billions of years before they eventually die, right? So you're already well into the age of the universe before the first stars are dying to form stellar mass black holes, because we don't have stars which weigh 10 billion times the mass of the sun. At most, they're a few thousand times the mass of the sun, and those are very rare. So how do you form a big black hole? Well, you can collide black holes. So, 1 + 1 is almost equal to 2. Not quite, because they radiate away the gravitational waves, as you saw. But the universe is expanding, and it's accelerating in its expansion. So that means that everything is getting further and further apart every day. So that means is that per unit volume, the rate at which black holes can encounter each other is also decreasing. So it turns out that it's highly improbable that black holes could grow to 10 billion times the mass of the sun through merging alone, right? So then how do they get that big? So there are all sorts of theories. So some people think that, so we see these huge black holes in the center of galaxies. So the question is, does the black hole form first and then the galaxy around it? Or does the galaxy form and then the black hole forms later? We don't know. So James Webb Space Telescope, for example, is looking very, very far back in time to try and answer these kinds of questions. And they're looking at what are called proto-galaxies, so the very early galaxies. And the hope is that if we see 10 billion solar mass black holes very soon after the Big Bang, then we know they formed in the early universe. And they could have formed through the collapse of lots of clouds of dust and gas when stars were first forming. Or they could actually be primordial seeds from the Big Bang itself. We're not sure. Could be both. The key thing here, just to wrap up, because this is a question I could talk about all day. It's really at the heart of what I'm interested in too, is there's probably multiple channels through which these huge black holes could form. And we're only now starting to be able to actually look back far enough in the universe to start to answer these questions. So it's a great question. Thank you. Hi.
So we have a lot of data on the radiation, I'm assuming, of the matter, but do we have any on the matter specifically, like where it goes or how it behaves?
Mm-hmm. That's a very good question as well. So your question speaks to the fundamental properties of the matter itself. So what we're detecting is mostly what we call synchrotron radiation. So we know it's primarily electrons. But what we're also interested in is the actual, if you will, thermodynamic and microphysical properties of the matter. So this would be stuff like how dense are the electrons, the distribution of electrons in the plasma around the black hole. So it's about 10 to the 6 per centimeter cubed, so it's pretty dense. How strong are the magnetic fields? They're pretty strong, but relatively not that strong. They're about as strong as a fridge magnet, basically, a few milligauss or so. But they can be as high near the event horizon as tens to hundreds of Gauss, which is very strong. But compared to other objects in the universe, it's not that strong. But it's strong enough for the black hole to actually control the matter around it and for it to fall onto it. And so they are actually beautiful laboratories to test matter in the extreme regime. And so your question, the reason I said it's a good one is because we're constantly building bigger and bigger particle accelerators, like the LHC and CERN, for example, because we want to smash particles together to see what's produced. And we can probe physical regimes that we can't otherwise access. But black holes are the most extreme physical regime, where gravity dominates, where everything is just cranked up to 11. And so you can never build that in a lab. But we have these labs out there, laboratories out there in space.
Awesome. So we've got one final question up in the gallery somewhere, up on the left.
Hi. Hi.
Hi.
Thank you for today. I really appreciate it. I was trying to understand what you were saying about, I think you said about information being lost as it crosses the threshold. Yet there's a thermodynamic pair or something that gets radiated outwards. And what I was wondering was, if there's no information you can get out of a black hole, do you think that further study will be by physical observation or it's more mathematical?
I'm at the risk of sounding repetitive. It's another good question. So, as I mentioned briefly, thank you for your question. So, in the talk, I very briefly touched on Hawking's. So 1974 is where he established the notion of a virtual pair, one of which would be captured by the black hole, one of which would escape, and that would carry away a minute amount of black body radiation of thermal energy. Absolutely minuscule. But in 1971, so 3 years earlier, is where he did his seminal work, where he was able to establish that the entropy of a black hole is linearly proportional to the area of the event horizon. So what does that mean? So if you look at the actual equation, it's a fancy way of saying the entropy, so it's the measure of disorder or the information diffusion, in a sense, like of that black hole is spread over microstates of the surface of the event horizon. And those microstates, those area elements, if you imagine a sphere with lots of little triangles on it, each one of those triangles has a Planck area, and a Planck length is the absolute smallest physical scale that you can ever have, and we'll probably never be able to probe that scale, but each one of those Planck areas contains some bit of, like a bit of information, like a 1 or a 0. And for a typical solar mass black hole, that can be like 10 to the power 77 states just within a typical solar mass black hole. So some people think that the idea is that the black hole actually stores all of the information, past and present, of its history on those microstates. And as the black hole feeds and grows, those number of microstates grows rapidly, right? Because if you double the size of the black hole, then its area grows as its radius squared, so you can see that grows quadratically. So in short, whether or not we'll be able to measure that, I think it seems extremely unlikely, because you're probing physical scales that are just so minuscule. Even if the black hole was here on Earth, we wouldn't be able to do that. But there are people, so far this hasn't worked, who thought that actually a little bit of Hawking evaporation from merging binary black holes would lead to some kind of if you will, like perturbation or deviation from what we'd expect in a gravitational wave form. And it might be that through gravitational waves one day we might potentially, although I think it's unlikely, be able to see this. So this is really something that's, at least for now, it really is science fiction. So, but nonetheless, I should add, I'm sorry to take up so much time on this, but it's important. The reason Hawking looked into this is precisely for the reason you said about this causal boundary, because thermodynamics, right, you have a system, and a black hole is disconnected from the rest of the universe, but then the laws of thermodynamics don't apply, and that means it's violating the laws of thermodynamics. And so his work was really to help reconcile that, and it's very important foundational work.
Fantastic. A really mind-blowing question to finish on, and I think it's always good to hear that there's loads more stuff to be done in a field like this. So if you're sitting here and enjoyed the talk, maybe you can be standing here in 15 years' time telling everybody that we don't know anything about black holes as well. Fantastic. The wonderful Dr. Ziri Younsi, everybody.